So 13.6 cylinders and quadric surfaces. We are going to fun and play with graphs in space, some of them by hand, some of them I'll have to use GeoGebra to show you how this works, okay? Well, this is going to be one of the two surfaces we're going to look. Well, number one, the cylindrical surfaces, and then recognize and write equations of quadric surfaces, which is the 3D equivalent of what you know about of what you know as the conic section. Remember conics, the parabola, the ellipse, the hyperbola. So there are 3D versions of those. You'll see they're pretty cool. But what are cylindrical surfaces? Well, actually, these pictures you see on the definition box, they're cylinders. Like, but what? I mean, a cylinder. I thought it was something like that kind of, or like this one, right? That's what you know as a cylinder, isn't it? But no, actually, those are also cylinders. Well, how do we recognize that these are cylinders? Well, so we're going to be given an equation or a relation, if you will, with two variables, not three variables at a time. Two variables, one of the variables will be missing. So that essentially is going to give us a trace. All right, it's going to give us a trace in two dimensions. And these lines in blue, notice how they extend along, in this case, along the x-axis, creating what we call a cylindrical sheet, if you will, right? It's like a cylindrical sheet. And so, in this case, well, we have this y equals to z squared. Well, this looks a lot like a parabola, right? In this case, it looks like a sideways parabola, but it's only involving the y and the z axis. See what variable is missing? It's the x variable that's missing, so that's why these lines in blue are extending along the x-axis. Okay, so and that's what creates like a cylinder. Now, put that graph, that sheet, like vertically, if you will. That's going to look somehow like a cylinder, but with a parabolic shape in this case. Okay. Let's draw this by hand. Okay, let's do some of this. Okay, let's sketch the surfaces represented by the given equations. Okay, so describe the generating curve and identify the axis to which each cylinder is parallel. Okay, so here it is. All right, y equals x squared. I mean, this is just the basic parabola you know from algebra, right? Okay, but we need to turn this into 3D, okay? That means, so let me do a 3D sketch here. But before I plot the surface in space, I'm going to plot its projection into dimensions. All right. Observing this equation right here, which variable is the independent variable? Is it x or is it y? X. Okay, so our inputs will be x, our outputs will be y. And well, I mean, this is the parabola you already know, I know, right? So now, how are we going to transfer, so to speak, that picture to the space? Well, let me extend is to the negative, all right? And well, so this graph into dimensions is what we would be seeing from the top view in space right here. So this looks like the parabola. It looks like this. It looks a little bit like this, all right? Agree with this? This is what you would see. Well, number one, okay. What variable is missing out of the three? So that means this parabola will extend along the z-axis. I'm gonna draw another parabola like this, and I'm going to draw these lines to create the cylindrical sheet. Right? So that's one example of how we plot this in 3D. Let's do another one. Okay. x squared plus z squared equals to 4. What does that remind you of?
Equation of a circle.
It's the equation of a circle, right? But I mean, yes, it's a circle involving the variables x and z, not the x and y like the regular circle you know from analytic geometry, right? Well, that means, okay, let's plot it in space. Oops. So that's the x-axis, the y-axis, and the z-axis. So, okay, x squared plus z squared equals to 4. So that's a circle indeed. But what axes are involved in the equation of the circle? Aren't they the x and the z? So I'm going to plot a circle. I'm going to try my best and plot a circle involving the x and the z axis. Notice the missing variable is this time y, isn't it? So that means I'm going to draw another circle at another point on the y-axis. That means this circle right here. So this is going to give us the following. Well, that's actually a cylinder like the ones we know, right? This is legit the regular cylinder, right? But in this case, it's extended along the y-axis. So if we had the equation, say x squared plus y squared, the regular one, that would be a cylinder extending along the z-axis, all right? Even trigonometric functions can give rise to cylinders, and that's the case for letter C, all right? So, how is that going to work? How are we going to graph a trigonometric function? Number one, what variables are involved? So here we have the variable y and the variable z. In this case, the independent variable is y. The dependent variable is it's z. And in this case, notice I'm not using the f notation because the f notation wouldn't make it clear about what the dependent variable is. It z in this case? I mean, if I do this, for instance, f of y equals sine y, right? But it's not clear which variable is the dependent one. Is it z or is it x, right? So that's why we're keeping the other notation to make it clear which one is it. So that means I would need to first graph a trace of the sine function on the y-z plane. That is, this plane right here. So, well, I mean, you know the graph for sine, right? That looks like this. So I'm going to do the same here. Now, since this time it is the x variable that is missing, that means this sheet will be formed along the x-axis. That is, let me do another sign right here. And that's going to give us this sheet right here, all right? This cylindrical sheet in the form of a trigonometric function that is sine y, all right? All right, so that's about the cylindrical surfaces, the first kind of surfaces. Let's talk about the second kind of surfaces, quadric surfaces. Well, so where did these come from? Well, number one, let's define let's go back and review the conic sections. Well, so the conic sections are the intersections of two cones and the plane. So that's what gives rise to the four conic sections. Well, actually, yeah, that's four conic sections. Number one, the parabola, the circle, the ellipse, and the hyperbola. So we identify a parabola when only one of the variables is raised to the second power. We recognize a circle. Well, actually, we distinguish between a circle and an ellipse because both of them have the two variables raised to the second power. What else? They're both positive. However, when the denominators or the coefficients are different, in this case we have an ellipse. So you could say that a circle is a special case of ellipse where their coefficients or denominators are all the same. All right, and the hyperbola is distinguished from the ellipse. Yes, both variables are raised to the second powers. The denominators may or may not be the same. However, one of those terms is it's actually negative. All right, well, let's have a look at this. Let's talk about this equation in general. So that's the general second degree equation in two variables that gives rise to the conic sections. Except that in our beginning, or rather our intermediate algebra, or even in our pre-calculus course, we consider this equation for the case where b equals to 0. I'm going to talk about this in a second. So that means we can use the conic sections for coefficients a, c, d, e, and f. Right? So what is this b term? So this b term is actually a rotation term. So, and that's what gives rise to what we call the degenerate conic sections. What are they? For instance, you could, okay, if you have this ellipse, for instance, you could rotate the ellipse, say 45 degrees, 60 degrees, your favorite angle. But what operation is it's required to do such thing? Well, actually, that's something you may get to see in linear algebra. Actually, you set up a matrix with the coefficients of the conic sections. Then you do a matrix operation with some trigonometric entries to come up with new values that are going to be there. And actually, this degenerate conic sections have the xy term. None of the conic sections that you have worked before have this xy term. They're either x or x squared or y squared, but I'm pretty sure you haven't worked with this degenerate conic section. All right, actually, you have worked with one of those degenerate conic sections, but maybe you didn't know about it. All right? Let me show you. So, what about y equals to 1 over x? What's the graph of this? Doesn't that look like this? Right? You've used that graph, that function, pretty much every day in calculus, right? But did you see that this is a hyperbola? It's a hyperbola, but this is rotated 45 degrees, right? Just twist it 45 degrees and you're going to get a regular hyperbola that looks like this, right? Now, if you solve for this equation, if you rearrange this equation, multiply both sides by x, that's xy equals to 1. What do we have? The xy term, isn't it? So in a way, you have already worked with a degenerate conic section. In particular, this hyperbola, this unit hyperbola rotated 45 degrees. All right? Now, so the equations of the quadric surfaces. So now we're going to put our 3D glasses this time. So we're going to look at the quadric surfaces. These are going to be still second degree equations, but this time in 3 variables. Let's have a look at this. So ax squared plus by squared plus z squared. So now we have the third variable, the product terms, which again we're going to look at the cases where d, e, and f are all equal to 0 because we're not going to degenerate these surfaces for now. All right, and then we have the linear terms, that is the terms where they're raised to the first power, g, h, and I, and the constant term. Well, how do this look like? Okay, let's go to the very last page of that handout right here. And here we have a summary of the different quadric surfaces. Well, so the first one, the ellipsoid. This is what we call an ellipsoid, where all the traces are going to be ellipses. We're going to get back to the traces in the same way we did it for the graphing of the plane. We're going to graph some of these surfaces. Well, I'm going to use GeoGebra for this. It's kind of hard to do this by hand. Well, let's recognize and find some resemblance with the conic sections. Okay, do you see how these are all quadratic terms? They're all positive. And look at the denominators. They're different. A, B, and C, they're different. But what if A, B, and C were all the same? What surface would that be? I'll give you a hint. When you have an ellipse, and if the denominators or the coefficients are all the same, that's a circle. So what about an ellipsoid? What would that be? A sphere, right? So that'll be a sphere. Okay, let's talk about the elliptic parabola. And well, you might argue, well, are all paraboloids elliptic? Aren't there like circular paraboloid? Well, yes, but because again, a circle is a special case of ellipse. But to generalize the idea, we call it elliptic paraboloid. So how can we recognize this paraboloid? Well, let me get rid of this term for a second. Z equals to x squared divided by some number. Doesn't that look like the equation of, the equation of a parabola? Well, add another term to make it three-dimensional, all right? And again, in just the same way as we recognize a parabola by having one of the variables to be raised to the first power, here for the paraboloid, at least one of the variables is what's it called? It's raised to the first power, in this case z, but of course it could be x, it could be y. And by the way, notice how this ellipsoid opens along the z-axis. That's because it's solved for z. That's the variable raised to the first power. If you had instead y equals to x squared over a squared plus z squared over b squared, how would this paraboloid look like? We would open to along which axis? The y-axis, right? Like in this direction, right? Like this, all right? So we don't have to look at all the cases. I think this you can follow the pattern. Let's have a look at the next one. Hyperboloid of one sheet. So actually there's two hyperboloids. Number one, a hyperboloid of one sheet. Well, how do we recognize a hyperbola in the conic sections? They're all quadratic terms except that one of them is negative. Don't we have this here? Okay. How do we recognize a hyperboloid of one sheet versus a hyperboloid of two sheets? Okay. This minus sign, think of it as a sheet. How many sheets do we have in our formula? One, right? How many do we have here? Two. So that's a good way to distinguish them, all right? Elliptic cone. So, and in this case, we may or may not have both sides of the cone, the top and the bottom one. Well, we're going to use these cones later when we get to the triple integrals. But for now, we're just having a look at how these surfaces look like, what are the equations. And the last one, the hyperbolic paraboloid. Well, this is an interesting one. It's a hyperbola combined with a parabola. How is that? Because, okay, look at this. And look at that. From the top, doesn't that look like a hyperbola? And over here, what do we have? We have the parabola in this case. That looks like a saddle. That's what we will later discuss these saddle points, you know, and when we get to maximum and minimum values. Remember those problems where you use the second derivative test in Calc 1? Well, those are going to come back later here in Calc 3, but with 2 and 3 variables, and it's going to be fun. All right, you're going to like this. Yep. So, yeah, that looks a lot like a saddle or like a Pringles chip. You know, you look at the very center of a Pringles chip, that's a saddle point, a point where you have a minimum in one direction, but a maximum in the other direction, which is what we have here. Let me erase this to show you that. So here we have a minimum, but this is also a maximum in that direction. So there's no such thing as minimum and maximum at the same time. We call it a saddle point, all right? Okay. How about we work with a couple of examples where we use this conic section, quadric surfaces. By the way, you guys are not required to memorize these equations. Actually, you don't need to write this on your sheet of notes, just so you guys save space on your sheet of notes on the exam. So if I ask a question about any of these surfaces, I will give you the equation, I will give you the name of the surface. In the end, I will just ask you some information about it, like give me the traces, give me the intercepts or something, not like memorize so you can identify, okay? All right, let's have a look at one example. Two examples. Classify the surface 4x squared plus 4 9y squared minus z squared minus 36. Then describe the traces in the planes parallel to the coordinate planes, and then sketch the surface in the 3D space. All right. Oftentimes you will be given an equation like this that we need to do a little bit of work before we can identify it as any of the 6 quadric surfaces. Well, but I mean, judging by the coefficient, I think that gives it away, right? What would you think it is? It's kind of a sphere, but not quite a sphere. Close. It's an ellipsoid, right? All variables are squared, no variables to the first power, and all the coefficients are different. Well, we're going to work this equation to make it look like the actual generic form. Well, so I'm going to move the 36 to the right hand side. That gives us 4x squared plus 9y squared plus z squared equals to 36. And well, I'm going to divide both sides by 36 because our generic form calls for a 1 on the right hand side of the equation. So doing it so, that's going to give us, 4 over 36, that's x squared over 9, plus y squared over 4, plus z squared over 36 equals to 1. And indeed, this is an ellipsoid. Okay? This is an ellipsoid. Okay, they're asking us to describe the traces in the planes parallel to the coordinate planes and then sketch the surface. Doing it by hand. I'm not going to do it by hand again. I'm going to do it using GeoGebra. Okay, the traces. So last time we found the traces of a plane as well as the intercept. Recall, for the intercepts we need to peekaboo 2 variables at a time, and for traces we only peekaboo 1 of the variables. Okay, so let's get the xy trace. We obtain the xy trace by making z equals to 0. So that's going to give us x squared over 9 plus y squared over 4 equals to 1. The y z trace. Notice the missing variable is x, so that means we make x equals to 0. So that's going to give us the equation y squared over 4 plus z squared over 36 equals to 1. And lastly, make some space here. Lastly, the xz trace. That means, well, y is missing in the name of the trace, so that means we make y equals to 0. So that's going to give us x squared over 9 plus z squared over 36 equals to 1. Okay, let's forget about the surface in space. Let's talk about the traces and identify this time, since these are only equations in 2 variables. Let's identify the corresponding conic sections. So, what are the conic sections describing these equations? What are these? Ellipses. So this is an ellipse, right? What about the YZ trace? Also an ellipse, right? And lastly, the XZ trace, another ellipse, right? So 3 ellipses will form an ellipsoid. How is that going to happen? Well, let me go to GeoGebra. Okay, ellipsoid traces. Okay, so The first trace, this is, well, let me show you the equations and briefly explain what are these. So I'm using the parametric equations of the ellipse, that is using cosines and sines, but with different coefficients. If we had the same coefficients on the trig functions, then we would be graphing parametric circles, not parametric ellipses. But in this case, because of the coefficients, so you might remember this from Cal 2. So notice in this case, I have inputs in the x and the y component, but a 0 in the z component. That's because that's going to create our xy trace. So let me, you see the ellipse? All right. So that's the xy trace, the trace involving the x and the y axis. Now, the YZ trace, notice I have x equals to 0, y, and z, and then I'm going from 0 to 2 pi just to have these traces to be traversed only once. Okay, so that's the xy trace. Did you see how the y and the z axis gives us an ellipse? In the same way, the xy gives us another ellipse. Okay, what about the next one? Okay, so the x and z where y and z equals to 0. So let me go and change the graph where we have x and z as a perspective. Another ellipse. So these three traces right here create like the armor of the solid, if you will. All right? Let me show you that solid. That's simply the equation we're given. That's what it is. Okay, let me dim the light a little bit so you can see it better. So, okay, it takes a little long. Okay, so let me rotate the solid so you can see how the traces are exactly on the edge of the solid. So from either perspective, I'm going to upload these GeoGebra files to Canvas so you guys can visualize it at home. So you can create your own as well if you want to make some modifications as well. All right, so that's one example. Of course, think about it. Drawing these by hand, I'm not going to expect you to draw these by hand. Some of them I will ask you to draw by hand. Maybe one of those cylindrical sheets, something easy to plot. Maybe a cone, for instance. I'm going to ask you to draw a cone, for instance. A plane for sure. But when it comes to ellipsoids, hyperboloids, or the hyperbolic paraboloid, that saddle, it's kind of hard to plot by hand. Okay, so let's go back and have a look at one more example and wrap up this section. So classify the surface for y minus x squared equals to c squared. Then describe the traces in the planes parallel to the coordinate planes. Basically repeat the previous exercise with a different equation. And again, we're given the equation with the variables like all over the place. We need to make it look, we need to work on the equation a little bit to make it look like one of the equations in the summary at the end of the handout. All right. Well, how do we arrange this equation? What variable do we solve for? Do we solve for y? Do we solve for x? Or do we solve for z? Well, so you definitely don't want to solve for one of the variables that are raised to the second power, because if you do that, you would end up using the square root property, giving you a plus minus radical. And well, notice that's not what we have in our summary. So the easiest way here is just solve for the one that is raised to the first power. I'm going to solve for y in this case. Okay, so I'm going to move the negative x squared to the right hand side. So that's 4y equals to x squared plus y squared. Divide both sides by 4. That's x squared over 4 plus y squared over 4. Okay? That looks like a paraboloid, doesn't it? How do we know? Yes.
I think it's supposed to be z squared.
Yes, it's z, right? Yep. Thank you. Z. Thanks. So that looks a lot like a paraboloid. Well, how do we know? Well, comparing with the summary of equations at the end of the page, or simply by looking individually. I mean, by looking at the equations with two variables at the same time. For instance, like this. Looks a lot like a parabola, right? Like that also looks like a parabola, but involving different axes, right? Okay, so let's get the traces. So the xy trace. For the xy trace, we make z equals to 0. That is y equals to x squared over 4. Identify the conic section. Well, we already did, right? It looks a lot like a paraboloid. What's the next one? The YZ trace. The YZ trace, where we make x equals to 0, that's going to give us y equals to z squared over 4, which again, that's another paraboloid. The next one is a little tricky. The XZ trace. The XZ trace, well, what about it? So we need to make the y equals to 0, right? That doesn't seem like the hardest thing in the world. However, we are going to run into what it looks like a dead end because, okay, 0 equals to x squared over 4 plus z squared over 4. X squared, z squared, what's that? And a 0 on the left hand side. So we would need to think of all the order pairs x, z that add up together, raised to the second power, and divide by 4 gives 0. There's only one possibility, isn't it? This is only true for x equals 0 and y equals to 0. So that's going to give us simply the order triple that describes the origin. 0, 0, 0. Yes? Z equals to 0. So yeah, we already, yes, z equals to 0. That is, this one is a z, right? Yeah. So x equals 0, z equals 0. Substitute there, you're going to get y equals to 0. So that's simply the origin in space. Let's have a look at this in GeoGebra. Okay? So let me open GeoGebra 3D. So paraboloid traces. Okay. So the what was that? The XY trace. That is that second curve right here where I have an expression for x, an expression for y. Notice I'm using parametric equations. I'm not using x's and y's. I'm using t's. Notice there is a 0 for t, and I'm declaring the variable t. And the limits can be, well, since this is not a circular trajectory, this is going to be another kind of curve. You can go between -10 and 10. In this case, I chose my traces to go between t equals to -5 and 5. So that's going to give us this parabola on the xy plane. All right. What about the second trace? This is going to be the YZ trace. Nothing 0 for x. So that means, let me put the 3D graph so I can see the y and the z axis. That's going to give us the following graph. All right. And while I'm not going to type the point, the 0, 0, 0, I think it's pretty obvious, right? So this is pretty much the armor of the solid, all right? Now let me show the equation of the surface. And that's how it looks like, right? That's how it looks like. You can see the traces that are pretty much on the edge of the solid, all right? It's like those solids of revolution, remember from Calc 1 or Calc 2 or whatever you learned that? But we're not rotating that, okay? So we are creating these surfaces by means of traces, not by rotation. All right, go back to the notes, and I believe this is the end of the section, right?